What if everything we see in the universe, the stars, the galaxies, the vast cosmic expanse is just the tip of the iceberg? What if the true backbone of reality, the invisible force shaping everything we know, is something we can't even see? This is the enigma of dark matter, a mysterious substance that makes up more than 80% of the universe's mass, yet remains hidden from our eyes. Welcome to the cosmic dark matter era, a time in the universe's history where the unseen reigns supreme, and the rules of physics as we know them are rewritten. Over the next few minutes, we're diving deep into 25 of the most mind-bending mysteries surrounding this elusive cosmic phenomenon. From the invisible web that connects galaxies to the strange particles that might make up dark matter, each mystery will challenge what you think you know about the universe. So, are you ready to explore the shadows of the cosmos? Let's begin. Now turning to the first mystery, let's unravel the invisible web of dark matter. Picture the universe not as a collection of isolated galaxies, but as a vast, interconnected network like a cosmic spiderweb stretching across the cosmos. This is the cosmic web, a structure made up of dark matter filaments that act as the scaffolding of the universe. These invisible threads connect galaxies, guiding their formation and movement over billions of years. But here's the catch: we can't see it directly. Dark matter doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. So how do we know it's there? Through its gravitational effects, galaxies move in ways that can only be explained if there's an unseen force pulling them, and that force is dark matter. Simulations of the cosmic web show these filaments as a delicate, intricate network, with galaxies clustered at the intersections like beads on a string. Yet, despite its crucial role in shaping the universe, the cosmic web remains one of the most puzzling aspects of dark matter. Why does it form this specific structure? How does it influence the evolution of galaxies? And what secrets does it hold about the universe's origins? These questions drive scientists to probe deeper into the shadows of the cosmos, searching for answers hidden within the invisible threads of the cosmic web. Now shifting our focus to the second mystery, let's tackle the puzzling case of the missing baryons. Baryons are the building blocks of ordinary matter, everything from stars and planets to the air we breathe. According to cosmological models, the universe should contain a specific amount of baryonic matter. But here's the twist: when scientists tally up all the observable baryons, they find a significant shortfall. A large portion of this ordinary matter seems to have vanished without a trace. So where could it be hiding? One leading theory points to the warm-hot intergalactic medium, often abbreviated as WIMP. This elusive substance is a diffuse, superheated gas that fills the vast spaces between galaxies. It's so hot and thin that it's nearly invisible to our telescopes, making it incredibly difficult to detect. Yet, simulations suggest that this WIMP could account for a substantial fraction of the missing baryons. Another possibility is that some baryons are hiding in low-density regions of the universe where they're too faint to observe directly. Or perhaps they're locked away in massive cosmic structures like galaxy clusters, where their presence is masked by the overwhelming glow of other matter. The mystery of the missing baryons challenges our understanding of the universe's composition and raises questions about how matter is distributed on the largest scales. As scientists continue to refine their tools and techniques, they inch closer to uncovering the truth behind this cosmic enigma. What will they find? And what will it reveal about the universe's hidden architecture? The search for the missing baryons is far from over, and every discovery brings us one step closer to solving this cosmic puzzle. Now turning to the third mystery, let's explore the pivotal role dark matter plays in the formation of galaxies. Imagine the universe in its early stages, a chaotic sea of particles and energy. Without dark matter, this cosmic soup might never have coalesced into the galaxies we see today. Dark matter, with its gravitational pull, acted like an invisible scaffold, drawing ordinary matter together and providing the framework for galaxies to form. But here's the catch: while dark matter's gravitational influence is undeniable, its interaction with ordinary matter remains a mystery. Unlike the particles we're familiar with, dark matter doesn't emit, absorb, or reflect light, making it nearly impossible to observe directly. This lack of interaction poses a significant challenge for scientists trying to understand how dark matter and ordinary matter work together to build the universe's structures. One of the biggest questions is how dark matter's distribution affects the shape and size of galaxies. Simulations suggest that dark matter halos vast, invisible clouds surrounding galaxies play a key role in determining a galaxy's structure and evolution. Yet, mapping these halos and understanding their precise influence is no easy task. Another puzzle is why some galaxies seem to have more dark matter than others, and how this imbalance affects their development. As researchers continue to study these cosmic puzzles, they're uncovering clues about the delicate dance between dark matter and ordinary matter. What will these discoveries reveal about the origins of galaxies? And how might they reshape our understanding of the universe's grand design? The answers lie hidden in the shadows of dark matter, waiting to be brought into the light. Now shifting our focus to the fourth mystery, let's delve into the nature of dark matter particles themselves. What exactly is dark matter made of? This question has puzzled scientists for decades, and while we've made progress, the answer remains just out of reach. One of the leading candidates is something called weakly interacting massive particles, or WIMP. These hypothetical particles are thought to be heavy, slow-moving, and interact with ordinary matter only through gravity and possibly the weak nuclear force. Their elusive nature makes them incredibly difficult to detect, but if they exist, they could explain much of the dark matter in the universe. Another promising candidate is the axion, a much lighter particle that was originally proposed to solve a different problem in particle physics. Axions are theorized to interact even less with ordinary matter than WIMP, making them even harder to find. Despite their differences, both WIMP and axions share one thing in common: they've managed to evade detection so far. Scientists have built incredibly sensitive experiments deep underground, shielded from cosmic rays and other interference, to try and catch a glimpse of these particles. Yet, after years of searching, no definitive signal has been found. This raises an intriguing question: are we looking in the right place, or is dark matter something even stranger than we've imagined? Some researchers have begun exploring alternative theories, such as dark matter being made up of primordial black holes or even particles from extra dimensions. The search for dark matter particles is far from over, and every experiment, every theory brings us one step closer to uncovering the truth. What will it take to finally detect these mysterious particles, and what will their discovery mean for our understanding of the universe? The answers may lie in the next breakthrough, waiting to be uncovered in the depths of space or the heart of a laboratory. Now turning to the fifth mystery, let's explore one of the most compelling pieces of evidence for dark matter's existence: the bullet cluster. This cosmic phenomenon is actually the result of two galaxy clusters colliding at incredible speeds, creating a scene that looks like a cosmic bullet piercing through space. But what makes the bullet cluster so special isn't just the collision itself. It's what happened to the dark matter during this event. When these clusters collided, the ordinary matter, like gas and dust, slowed down due to friction and piled up in the center. However, the dark matter didn't behave the same way. Instead, it kept moving, passing right through the collision as if it weren't even there. This separation between ordinary matter and dark matter was captured by astronomers using a technique called gravitational lensing, which maps the distribution of mass by observing how light bends around massive objects. The result, a clear picture showing that most of the mass in the bullet cluster, the dark matter, wasn't where the visible matter was. This observation is a game changer because it provides direct evidence that dark matter exists and behaves differently from ordinary matter. It doesn't interact with light or other forms of electromagnetic radiation, and it doesn't collide or slow down like gas and dust. The bullet cluster is like a cosmic fingerprint, leaving behind clues about dark matter's elusive nature. But it also raises new questions. Why doesn't dark matter interact with ordinary matter in the same way? What forces govern its behavior, and what does this mean for our understanding of the universe? The bullet cluster isn't just a snapshot of a cosmic collision. It's a window into the invisible forces shaping our universe, and it reminds us just how much we still have to learn about the mysterious dark matter that surrounds us. Now shifting our focus to the sixth mystery, let's delve into how dark matter plays a pivotal role in the expansion of the universe. The rate at which the universe is expanding, often measured by the Hubble constant, has been a subject of intense debate among astronomers. Interestingly, dark matter is at the heart of this cosmic puzzle. While we know that dark matter makes up a significant portion of the universe's mass, its influence on the expansion rate is still not fully understood. Observations of distant galaxies and supernova suggest that the universe is expanding faster than some models predict, creating a tension between different measurements of the Hubble constant. This discrepancy could be a clue about dark matter's behavior. Some theories propose that dark matter might interact with itself or with other forces in ways we haven't yet detected, subtly altering the expansion rate. Others suggest that dark energy, the mysterious force driving the acceleration of the universe's expansion, might be intertwined with dark matter in ways we're only beginning to grasp. The challenge lies in reconciling these observations with our current understanding of physics. Could dark matter be slowing down or speeding up the expansion in ways we haven't accounted for? Or is there something fundamentally missing from our models of the cosmos? This tension not only highlights the complexity of dark matter, but also underscores how much we still have to learn about the forces shaping the universe. As we continue to refine our measurements and explore new theories, the relationship between dark matter and cosmic expansion remains one of the most intriguing mysteries of the cosmic dark matter era, reminding us that the universe is far more dynamic and enigmatic than we ever imagined. Now turning to the seventh mystery, we encounter one of the most fascinating gravitational enigmas in the cosmos, the Great Attractor. Imagine a colossal force hidden in the depths of space, pulling entire galaxies, including our own Milky Way, toward it at astonishing speeds. This invisible powerhouse, located in the direction of the constellations Centaurus and Hydra, has puzzled scientists for decades. What makes the Great Attractor so mysterious is that it lies behind the plane of our galaxy, obscured by dense clouds of dust and stars, making it incredibly difficult to observe directly. But here's where dark matter enters the picture. Scientists believe that the immense gravitational pull of the Great Attractor could be fueled by an enormous concentration of dark matter. This unseen material, which makes up most of the universe's mass, could be acting as the cosmic glue, creating a gravitational well so deep that it draws galaxies toward it like a cosmic magnet. Yet, despite its apparent influence, the Great Attractor remains poorly understood. Why is it so massive? How did it form? And what role does dark matter play in its behavior? Some theories suggest that the Great Attractor might be part of an even larger structure, like a supercluster of galaxies, with dark matter weaving an intricate web that binds it all together. Others propose that dark matter's unique properties could be amplifying its gravitational effects in ways we're only beginning to comprehend. The challenge lies in peering through the galactic dust and unraveling the secrets of this cosmic giant. As we continue to map the universe and refine our understanding of dark matter, the Great Attractor stands as a reminder of how much we still have to learn about the forces shaping our cosmic neighborhood. It's a mystery that not only captivates astronomers but also invites us to ponder the hidden structures that govern the universe's grand design. Now shifting our gaze to the eighth mystery, we delve into the enigmatic structures known as dark matter halos. Picture a galaxy not as a solitary island of stars, but as the glowing center of a vast, invisible cocoon. This cocoon is the dark matter halo, an immense sphere of unseen material that envelops galaxies and extends far beyond their visible edges. These halos are not just passive bystanders, they play a crucial role in shaping the fate of galaxies. Without them, galaxies as we know them might not even exist. The gravitational pull of dark matter halos acts like an invisible scaffold, holding galaxies together and influencing their rotation, formation, and evolution. For instance, the way stars orbit the center of a galaxy is largely dictated by the distribution of dark matter in its halo. But here's the catch: we can't see these halos directly. They don't emit light, nor do they interact with it, making them nearly impossible to observe with traditional telescopes. So how do we know they're there? Scientists rely on indirect methods, such as studying the motion of stars and gas within galaxies or observing the bending of light from distant objects, a phenomenon known as gravitational lensing. These techniques reveal the presence of dark matter halos by showing how their gravity affects the visible universe. Yet mapping these halos is no easy task. Their structure is complex, often described as lumpy or clumpy, with dense regions and voids that challenge our understanding of how dark matter behaves. Some halos appear to be smooth, while others show signs of substructures, like smaller clumps of dark matter orbiting within the larger halo. This variability raises questions about how dark matter halos form and evolve over time. Are they uniform across the universe, or do they differ from one galaxy to another? And what does their structure tell us about the nature of dark matter itself? These are questions that continue to puzzle astronomers as we refine our tools and techniques. From advanced simulations to next-generation telescopes, we inch closer to unraveling the secrets of dark matter halos. They remain a cornerstone of modern cosmology, a reminder that the universe's most influential forces are often the ones we cannot see. With each discovery, we gain a deeper appreciation for the invisible architecture that shapes the cosmos. Now turning to the ninth mystery, we find ourselves at the heart of our own galaxy, where an intriguing signal has captured the attention of scientists worldwide. The Fermi Gamma Ray Space Telescope, orbiting Earth since 2008, has detected an unusual excess of gamma rays emanating from the center of the Milky Way. Gamma rays are the most energetic form of light, often produced by extreme cosmic events like supernova or the collision of particles. But this particular signal doesn't fit neatly into any known category. It's a persistent, unexplained glow that has sparked one of the most tantalizing questions in modern astrophysics. Could this be evidence of dark matter annihilation? The idea is both fascinating and controversial. Dark matter, as we've discussed, doesn't interact with light, making it invisible to traditional telescopes. However, some theories suggest that dark matter particles could collide and annihilate each other, producing gamma rays as a byproduct. If this is happening at the center of our galaxy, it could explain the excess detected by Fermi. The signal aligns with predictions made by certain dark matter models, particularly those involving weakly interacting massive particles, or WIMP. These hypothetical particles are among the leading candidates for dark matter, and their annihilation could theoretically produce the gamma rays we're seeing. But before we jump to conclusions, it's important to note that this signal is far from confirmed as dark matter. There are other potential explanations, such as a population of rapidly spinning neutron stars called pulsars, or even cosmic rays interacting with gas and dust in the galactic center. These alternatives are also capable of producing gamma rays, and distinguishing between them and dark matter annihilation is no simple task. scientists have been meticulously analyzing the data, looking for patterns or features that could point to one explanation over the other. For instance, if the gamma rays are coming from dark matter, their distribution should be smooth and symmetrical. If they're from pulsars, the signal might appear more clumpy or irregular. So far, the results remain inconclusive, keeping the debate alive. What makes this mystery so compelling is its potential to unlock one of the universe's greatest secrets. If the Fermi gamma ray excess is indeed linked to dark matter, it would be a groundbreaking discovery, offering the first direct evidence of dark matter particles and their behavior. But even if it's not, the investigation has already deepened our understanding of the galactic center and the complex processes at work there. As researchers continue to refine their models and gather more data, the Fermi gamma ray excess remains a tantalizing puzzle, one that could reshape our understanding of the cosmos. And with that, we move closer to the next mystery, where we'll explore how dark matter might be connected to the very fabric of the early universe. Now shifting our gaze to the very dawn of the universe, we encounter the 10th mystery, the profound connection between dark matter and the cosmic microwave background, or CMB. The CMB is often described as the afterglow of the Big Bang, a faint echo of light that fills the entire cosmos, dating back to when the universe was just 380,000 years old. This ancient light holds a treasure trove of information about the early universe, and hidden within its subtle patterns are clues about the nature of dark matter. To understand how dark matter influenced the CMB, we need to rewind to the universe's infancy. In those early moments, the cosmos was a seething, dense soup of particles and energy. Ordinary matter, the stuff that makes up stars, planets, and us, was tightly coupled with light, creating a plasma so dense that light couldn't travel freely. Dark matter, on the other hand, was already doing its own thing. Unlike ordinary matter, dark matter doesn't interact with light, so it was free to clump together under gravity's pull, forming the seeds of the cosmic structures we see today. As the universe expanded and cooled, ordinary matter and light finally decoupled, allowing light to travel freely for the first time. This moment, known as recombination, is what we see as the CMB. But here's where dark matter's role becomes crucial. The gravitational influence of dark matter had already begun to shape the distribution of ordinary matter, creating tiny fluctuations in density. These fluctuations left their mark on the CMB, imprinting it with a pattern of hot and cold spots that we can still observe today. By studying these patterns, scientists can infer the properties of dark matter. For instance, the size and distribution of the hot and cold spots tell us about the amount of dark matter in the early universe and how it interacted with ordinary matter. The CMB also provides insights into dark matter's temperature. If dark matter were warm, meaning its particles moved at higher speeds, it would have smoothed out these fluctuations more than cold dark matter, which moves more slowly. The CMB data strongly supports the idea of cold dark matter, aligning with many of our current cosmological models. But the CMB doesn't just tell us about dark matter's past, it also helps us understand its role in shaping the universe's future. The gravitational pull of dark matter continued to amplify those early density fluctuations, eventually leading to the formation of galaxies, clusters, and the vast cosmic web we see today. Without dark matter, the universe would look very different, and the CMB gives us a snapshot of how it all began. This mystery is a testament to the power of observation and deduction. By studying the faint whispers of light from the early universe, we can piece together the story of dark matter and its profound influence on the cosmos. And as we continue to refine our understanding of the CMB, we move closer to unraveling the secrets of dark matter and the universe itself. With this in mind, we now turn to the next mystery, where we'll explore a controversial experiment that claims to have detected dark matter particles directly. Now turning to a mystery that has sparked both excitement and skepticism in the scientific community, we explore the Dama/Libra anomaly. This experiment, conducted deep underground in Italy, claims to have detected dark matter particles through a unique method. The Dama/Libra team uses sodium iodide crystals to search for signals of dark matter interactions. Over the years, they've reported a consistent, repeating signal that seems to align with Earth's movement through the galaxy, suggesting the presence of dark matter particles. The idea behind the experiment is fascinating. As Earth orbits the Sun, it moves through the Milky Way's dark matter halo. If dark matter particles exist, they should occasionally collide with the atoms in the detector, producing a faint signal. The Dama/Libra team claims to have observed just that, a signal that fluctuates with the seasons, peaking in June and dipping in December. This seasonal variation is exactly what scientists would expect if dark matter were responsible. However, this discovery is far from universally accepted. Other experiments using different materials and techniques have failed to replicate the Dama/Libra results. Critics argue that the observed signal could be caused by other factors, such as background radiation or subtle changes in the detector's environment. The lack of independent confirmation has left many scientists cautious, and the debate over the validity of these findings continues to this day. If the Dama/Libra results are confirmed, it would be a groundbreaking discovery, providing the first direct evidence of dark matter particles. It would also open up new avenues for understanding the nature of dark matter, such as its mass and how it interacts with ordinary matter. But until other experiments can verify these results, the Dama/Libra anomaly remains one of the most tantalizing and controversial mysteries in the search for dark matter. As we move forward, the next mystery takes us deeper into the cosmos, where we'll explore the connection between dark matter and the formation of supermassive black holes, shedding light on how these enigmatic giants came to dominate the universe. Now shifting our gaze to the heart of galaxies, we delve into the intriguing relationship between dark matter and the birth of supermassive black holes. These cosmic giants, found at the center of nearly every galaxy, are millions to billions of times more massive than our Sun. But how did they grow so large, and what role did dark matter play in their formation? This is one of the most compelling questions in modern astrophysics. One leading theory suggests that dark matter provided the scaffolding for the first supermassive black holes. In the early universe, dark matter's gravitational pull gathered ordinary matter into dense clumps, creating the seeds for galaxies. Within these clumps, gas and dust collapsed under their own gravity, forming the first stars and eventually black holes. Dark matter's influence didn't stop there. As these black holes grew, they continued to feed on the surrounding dark matter, which funneled more material into their grasp. Over billions of years, this process could have led to the formation of the supermassive black holes we observe today. Another fascinating idea is that dark matter itself might have directly contributed to black hole formation. Some theories propose that dark matter particles could clump together in such high densities that they collapse into black holes without the need for stars or gas. These so-called primordial black holes could have formed in the early universe long before the first stars ignited. If they merged or grew over time, they might have become the supermassive black holes we see today. While this remains speculative, it opens up exciting possibilities for understanding the origins of these cosmic behemoths. The connection between dark matter and black holes also raises questions about their mutual influence. For instance, supermassive black holes are known to emit powerful jets of energy that can shape their host galaxies. Could dark matter play a role in fueling these jets or influencing their behavior? Some researchers believe that dark matter interactions near black holes could produce detectable signals, offering a new way to study both phenomena. As we continue to unravel the mysteries of dark matter and black holes, one thing is clear: these two cosmic enigmas are deeply intertwined. Whether dark matter acted as a cosmic architect, a direct contributor, or a silent partner in the formation of supermassive black holes, its role remains a key piece of the puzzle. And with each new discovery, we inch closer to understanding how these giants came to dominate the universe. With this mystery explored, we now turn our attention to another fascinating aspect of dark matter, the elusive process of dark matter annihilation, and why detecting it has proven to be such a challenge. Now turning to one of the most elusive processes in the cosmos, we explore the mystery of dark matter annihilation. This phenomenon occurs when two dark matter particles collide and destroy each other, converting their mass into energy. In theory, this process could produce detectable signals such as gamma rays or other high-energy particles. But despite decades of searching, scientists have yet to confirm its existence. Why is it so hard to detect, and what could it tell us about the nature of dark matter? One of the biggest challenges lies in the fact that dark matter doesn't interact with light or ordinary matter in the ways we're used to observing. Unlike stars or gas clouds, dark matter doesn't emit, absorb, or reflect light, making it invisible to traditional telescopes. To detect annihilation, researchers rely on indirect methods, searching for the faint traces of energy or particles that might be produced during the process. However, these signals are incredibly weak and often drowned out by other cosmic phenomena, such as supernova or pulsars. Another complication is the uncertainty surrounding the properties of dark matter itself. If dark matter particles are extremely massive, as some theories suggest, their annihilation might produce rare, high-energy events that are difficult to capture. On the other hand, if they're lighter, the signals could be too faint to distinguish from background noise. This uncertainty makes it difficult to design experiments that can definitively detect annihilation. Despite these challenges, scientists are not giving up. Experiments like the Fermi Gamma Ray Space Telescope and the Large Hadron Collider are actively searching for signs of dark matter annihilation. The Fermi telescope, for example, scans the sky for gamma rays that could be produced by dark matter collisions in regions like the center of the Milky Way, where dark matter is thought to be densely concentrated. Meanwhile, particle accelerators like the Large Hadron Collider aim to recreate the conditions of the early universe, hoping to produce and detect dark matter particles directly. If dark matter annihilation is ever detected, it could revolutionize our understanding of the universe. Not only would it confirm the existence of dark matter particles, but it could also reveal their mass, interactions, and even their role in shaping the cosmos. For now, the search continues, driven by the tantalizing possibility of uncovering one of the universe's best-kept secrets. As we move forward, our next mystery takes us to the vast cosmic voids, where dark matter's presence challenges our understanding of its distribution and behavior. Now shifting our gaze to the vast, empty expanses of the cosmos, we encounter the enigmatic void phenomenon. These cosmic voids are immense regions of space, spanning hundreds of millions of light-years, where galaxies are few and far between. Yet, despite their apparent emptiness, these voids are far from devoid of matter-dark matter, that is. In fact, dark matter seems to dominate these regions, weaving an invisible web that shapes the structure of the universe on the largest scales. The presence of dark matter in these voids challenges our understanding of how it is distributed throughout the cosmos. While we often think of dark matter as concentrated in halos around galaxies or clusters, its role in these sparse regions is equally significant. The voids act as cosmic laboratories, offering a unique environment to study dark matter's behavior in the absence of the dense, luminous matter we're more familiar with. Here, dark matter's gravitational influence is the primary force at play, subtly guiding the motion of galaxies on the edges of these voids and shaping the large-scale structure of the universe. One of the most intriguing aspects of cosmic voids is how they reveal the delicate balance between dark matter and ordinary matter. In regions where galaxies are scarce, dark matter's gravitational pull becomes more apparent, as there's less interference from the clumping of stars and gas. This allows scientists to observe how dark matter behaves in isolation, providing clues about its properties and interactions. For instance, the way galaxies on the outskirts of voids move can reveal how dark matter is distributed within these vast, empty spaces. However, studying these voids is no easy task. Their sheer size and the faintness of the signals they produce make them difficult to map and analyze. Advanced simulations and observations, such as those from the Sloan Digital Sky Survey, have been instrumental in uncovering the intricate relationship between dark matter and cosmic voids. These tools allow researchers to trace the invisible threads of dark matter that stretch across the universe, connecting galaxies and defining the boundaries of these immense empty regions. The void phenomenon also raises questions about the nature of dark matter itself. Why does it seem to dominate these regions? How does its distribution in voids differ from that in galaxy clusters? And what does this tell us about the early universe when these voids first began to form? These questions push the boundaries of our knowledge, challenging us to rethink our assumptions about dark matter's role in the cosmos. As we continue to explore these cosmic voids, we uncover not just the mysteries of dark matter, but also the profound interconnectedness of the universe. These vast, empty spaces remind us that even in the absence of light, dark matter's invisible hand is at work, shaping the cosmos in ways we are only beginning to understand. And with that, we turn our attention to another puzzle: how dark matter interacts with light, or rather, how it doesn't. Now, stepping into the realm of light and shadow, we encounter one of the most baffling aspects of dark matter: its refusal to interact with light. Unlike ordinary matter, which absorbs, reflects, or emits light, dark matter remains entirely invisible to our telescopes. This elusive behavior is what makes it so challenging to study directly. If dark matter doesn't interact with light, how can we even know it's there? The answer lies in its gravitational effects, which leave subtle but unmistakable fingerprints on the cosmos. One of the most powerful tools scientists use to detect dark matter is gravitational lensing. This phenomenon occurs when the immense gravitational pull of dark matter bends the path of light from distant objects, such as galaxies or quasars, as it travels toward us. Imagine looking through a warped glass. The light from behind the glass appears distorted, creating arcs, rings, or multiple images of the same object. By studying these distortions, astronomers can map the distribution of dark matter, even though it remains invisible. Gravitational lensing acts like a cosmic magnifying glass, revealing the hidden presence of dark matter in galaxy clusters and even in the vast voids we discussed earlier. But gravitational lensing isn't the only indirect method scientists use to study dark matter. Another approach involves observing the motion of stars and galaxies. In regions where dark matter is thought to dominate, such as the outer edges of galaxies, stars move faster than they should based on the visible matter alone. This discrepancy suggests the presence of an unseen mass dark matter exerting its gravitational influence. By measuring these unexpected motions, researchers can infer the amount and distribution of dark matter in a given area. The lack of interaction with light also raises intriguing questions about the nature of dark matter particles. Why don't they interact with photons, the particles of light? One leading theory suggests that dark matter particles might be electrically neutral, meaning they don't carry a charge that would allow them to interact with electromagnetic forces, including light. This would make them fundamentally different from the particles we're familiar with, such as electrons or protons, which do interact with light. Despite the challenges, the study of dark matter's interaction, or lack thereof, with light has led to groundbreaking discoveries. It has forced scientists to think creatively, developing innovative techniques to detect something that remains stubbornly invisible. From gravitational lensing to the motion of stars, these indirect methods have painted a picture of a universe woven together by dark matter's unseen threads. As we continue to unravel the mysteries of dark matter, its refusal to interact with light serves as both a barrier and a clue. It challenges us to look beyond what we can see, pushing the boundaries of our understanding and inspiring new ways to explore the cosmos. And with that, we turn our attention to another puzzle, the debate over whether dark matter is cold or warm, and what that means for the structure of the universe. Now shifting our focus to the temperature of dark matter, we delve into a heated debate that has puzzled scientists for decades. Is dark matter cold or warm? This seemingly simple question holds profound implications for our understanding of the universe's structure and the formation of galaxies. The temperature of dark matter refers to how fast its particles move, and this motion directly influences how it clumps together to shape the cosmos. Cold dark matter, as the name suggests, consists of particles that move relatively slowly. This sluggish movement allows it to clump together more easily, forming dense structures like galaxies and galaxy clusters. The cold dark matter model has been incredibly successful in explaining the large-scale structure of the universe, matching observations of galaxy distribution and cosmic filaments. However, it's not without its challenges. For instance, the cold dark matter model predicts an abundance of small satellite galaxies around larger ones, but observations show far fewer than expected, a discrepancy known as the missing satellite problem. On the other hand, warm dark matter particles move faster, making them less likely to clump together on small scales. This could potentially resolve the missing satellite problem by suppressing the formation of smaller galaxies. Warm dark matter is often associated with lighter particles, such as hypothetical sterile neutrinos, which could explain why we see fewer small galaxies than the cold dark matter model predicts. However, warm dark matter also struggles to fully account for the observed distribution of galaxies on larger scales, leaving scientists to weigh the pros and cons of each scenario. The distinction between cold and warm dark matter isn't just an academic debate, it shapes our understanding of how the universe evolved. If dark matter is cold, it suggests a universe where structures formed hierarchically, with small clumps merging over time to create larger ones. If it's warm, the story becomes more nuanced, with faster-moving particles smoothing out small-scale structures while still allowing larger ones to form. This difference could even influence the nature of dark matter itself, hinting at whether it's made of heavier, slower particles or lighter, faster ones. As scientists continue to explore this mystery, they rely on a combination of simulations, observations, and experiments to piece together the puzzle. From studying the distribution of galaxies to analyzing the cosmic microwave background, every clue brings us closer to understanding whether dark matter is cold, warm, or perhaps something in between. This debate not only deepens our knowledge of dark matter, but also challenges us to rethink how the universe came to be the way it is today. With this intriguing question still unresolved, we now turn our attention to another fascinating mystery, the possibility that dark matter might be connected to the multiverse, opening up a whole new realm of cosmic speculation. Now stepping into the realm of cosmic speculation, we explore a mind-bending possibility. Could dark matter be the key to unlocking the mysteries of the multiverse? The idea of a multiverse, a vast collection of parallel universes beyond our own, has long fascinated scientists and science fiction enthusiasts alike. But what if dark matter, the invisible force shaping our universe, is also the bridge connecting these other worlds? One intriguing theory suggests that dark matter might not just exist in our universe but could permeate multiple universes. In this scenario, dark matter particles could interact weakly across different dimensions, acting as a kind of cosmic glue that binds the multiverse together. This idea stems from the concept of extra dimensions, a cornerstone of string theory, which proposes that our universe is just one of many existing in a higher dimensional space. If dark matter exists in these extra dimensions, it could explain why it's so elusive in our own. It might be leaking into other universes, making it difficult to detect directly. Another speculative idea ties dark matter to the concept of brains, short for membranes, which are theoretical objects in higher dimensional space. According to this theory, our universe could be a brain floating in a higher dimensional bulk, and dark matter might be particles that can move freely between branes. This would mean that dark matter isn't just a local phenomenon but a cosmic traveler, influencing multiple universes simultaneously. If true, this could redefine our understanding of dark matter's role, suggesting it's not just a passive player in our universe but an active participant in a much larger cosmic drama. While these theories are highly speculative, they open up exciting possibilities for understanding dark matter's true nature. If dark matter is indeed connected to the multiverse, it could provide a way to test the existence of other universes indirectly. For example, anomalies in the distribution of dark matter or unexplained gravitational effects could be hints of interactions with parallel worlds. Experiments like those searching for dark matter particles or studying the cosmic microwave background might one day uncover evidence of these hidden connections. As we ponder these ideas, it's important to remember that the multiverse remains a theoretical concept, and the connection to dark matter is still in the realm of speculation. Yet, the very possibility that dark matter could be a bridge between universes challenges us to think beyond the boundaries of our own cosmos. It invites us to imagine a reality far more complex and interconnected than we've ever imagined. With this tantalizing mystery still unfolding, we now turn to another profound question. Where did dark matter come from in the first place? The origin of dark matter is a puzzle that takes us back to the very beginning of the universe, and it's a story we'll explore next. Now shifting our gaze to the very beginnings of the cosmos, we delve into one of the most fundamental questions about dark matter. Where did it come from? The origin of dark matter is a mystery that takes us back to the earliest moments of the universe, a time when the seeds of everything we see today were first sown. To understand dark matter's beginnings, we must journey to the cosmic dawn, just fractions of a second after the Big Bang. One leading theory suggests that dark matter was created during the universe's rapid expansion, a period known as inflation. During this time, the universe was a seething cauldron of energy, and particles were constantly popping in and out of existence. It's possible that dark matter particles formed during this chaotic phase, emerging as stable remnants of the universe's fiery birth. These particles, unlike ordinary matter, would have been immune to the forces that shaped the visible universe, allowing them to persist and accumulate over billions of years. Another intriguing idea ties dark matter's origin to the era of cosmic reheating, which followed inflation. As the universe cooled, it's thought that dark matter particles could have condensed out of the primordial soup, much like droplets forming from steam. These particles would have been incredibly massive, far heavier than any known particle today, and their sheer mass could explain why they interact so weakly with ordinary matter. This theory aligns with the concept of WIMP, weakly interacting massive particles, which remain one of the top candidates for dark matter. But the story doesn't end there. Some scientists propose that dark matter might have been produced during phase transitions in the early universe, similar to how water turns to ice. These transitions could have created regions of space with different properties, and dark matter might have emerged as a byproduct of these cosmic shifts. If true, this would mean that dark matter is not just a relic of the Big Bang, but a consequence of the universe's evolving structure. As we piece together these theories, one thing becomes clear. Dark matter's origin is deeply intertwined with the universe's own birth and growth. Its existence challenges us to rethink our understanding of the cosmos, pushing us to explore the very limits of physics. While we may not yet have definitive answers, each new discovery brings us closer to unraveling this ancient mystery. With the question of dark matter's origin still echoing in our minds, we now turn our attention to another fascinating aspect of its role in the cosmos: its contribution to the formation of cosmic filaments, the largest structures in the universe. This next mystery will take us even deeper into the intricate web of dark matter's influence. Now turning to the vast cosmic tapestry, we explore how dark matter plays a pivotal role in shaping the largest structures in the universe, cosmic filaments. These immense threads of matter stretch across billions of light years, weaving together galaxies and galaxy clusters into a sprawling network known as the cosmic web. But what exactly are these filaments, and how does dark matter contribute to their formation? At the heart of this mystery lies the gravitational influence of dark matter. In the early universe, tiny fluctuations in density created by dark matter acted as seeds for the growth of cosmic structures. Over billions of years, gravity amplified these fluctuations, pulling matter into dense regions and leaving behind vast, empty voids. Dark matter, with its immense gravitational pull, formed the backbone of this cosmic architecture, guiding ordinary matter into the intricate filaments we observe today. These filaments are not just empty lines in space, they are highways of gas and galaxies, connecting clusters like beads on a string. Dark matter's gravitational pull ensures that these filaments remain stable, even as the universe continues to expand. Without dark matter, the cosmic web as we know it would not exist, and the universe would look vastly different. However, observing these filaments directly is no easy task. Unlike galaxies or galaxy clusters, which emit light and other forms of radiation, cosmic filaments are incredibly faint and diffuse. Most of their mass is composed of dark matter, which doesn't interact with light, making them nearly invisible to traditional telescopes. Scientists rely on indirect methods, such as studying the gravitational lensing effect, where the immense mass of a filament bends the light from background objects, revealing its presence. Another approach involves mapping the distribution of galaxies, as they tend to align along these dark matter threads. Despite these challenges, recent advancements in technology and observational techniques have allowed us to glimpse the faint outlines of these cosmic threads. Simulations and observations combined have painted a clearer picture of how dark matter weaves the universe's largest structures together, yet much remains unknown. How do these filaments evolve over time? What role do they play in the formation of galaxies and the distribution of matter across the cosmos? As we unravel the secrets of cosmic filaments, we gain a deeper appreciation for dark matter's role in shaping the universe. These invisible threads not only connect galaxies but also tell the story of how the cosmos grew from a chaotic beginning into the structured, interconnected web we see today. With each discovery, we come closer to understanding the full extent of dark matter's influence on the universe's grand design. With this insight into the cosmic web, we now shift our focus to another intriguing aspect of dark matter: its remarkable stability over cosmic timescales. This next mystery will explore why dark matter appears to endure unchanged, even as the universe around it evolves. Now stepping into the realm of cosmic endurance, we encounter one of the most puzzling aspects of dark matter: its remarkable stability. Unlike ordinary matter, which can decay, transform, or interact in countless ways, dark matter seems to remain unchanged over billions of years. This raises a profound question: why does dark matter persist, seemingly immune to the forces that shape and alter everything else in the universe? To understand this mystery, we must first consider the nature of dark matter particles. If dark matter is made up of particles, as most theories suggest, they must be incredibly stable. Unlike protons or neutrons, which can break down or combine with other particles, dark matter particles appear to resist such transformations. This stability is crucial for their role in the universe's structure. If dark matter decayed or interacted frequently, the cosmic web of galaxies and filaments we see today would never have formed. One leading theory suggests that dark matter particles are their own antiparticles. This means that if two dark matter particles collide, they could annihilate each other, releasing energy. However, such collisions would be extremely rare given the vast distances between particles in the universe. This rarity could explain why dark matter remains stable over cosmic timescales. Another possibility is that dark matter particles are simply too massive to decay into lighter particles, making them effectively immortal. Another intriguing idea is that dark matter is governed by a symmetry principle, much like the conservation of energy or momentum in physics. This symmetry could prevent dark matter from decaying or transforming, ensuring its stability. Some theories even propose that dark matter is part of a hidden sector of the universe, governed by laws of physics we have yet to discover. In this scenario, dark matter's stability might be a consequence of these unknown laws. Despite these theories, the question of dark matter's stability remains unresolved. Experiments like those searching for dark matter annihilation or decay have yet to find conclusive evidence. This lack of detection only deepens the mystery, as it suggests that dark matter's stability is not just a matter of rarity, but perhaps a fundamental property of its nature. As we ponder the enduring nature of dark matter, we are reminded of how much we still have to learn about the universe's hidden components. Its stability is not just a scientific curiosity. It is a cornerstone of the cosmos, shaping the universe's past, present, and future. With each new discovery, we inch closer to unraveling this cosmic enigma, bringing us one step closer to understanding the true nature of dark matter. With this exploration of dark matter's stability, we now turn our attention to another fascinating puzzle, the missing satellite problem. This next mystery will delve into why the number of observed satellite galaxies around the Milky Way doesn't match our theoretical predictions, and how dark matter might hold the key to solving this cosmic discrepancy. Now shifting our gaze to the cosmic neighborhood of our own galaxy, we encounter a puzzling mismatch that has left astronomers scratching their heads: the missing satellite problem. According to our best models of the universe, the Milky Way should be surrounded by hundreds, if not thousands, of small satellite galaxies. Yet when we look up at the night sky, we only observe a fraction of that number. Where are all these missing galaxies, and what role does dark matter play in this cosmic discrepancy? To understand this mystery, we need to dive into the predictions made by the lambda-cold dark matter model, the leading framework for understanding the universe's structure. This model suggests that dark matter forms halos around galaxies, and these halos should host numerous smaller satellite galaxies. However, observations reveal far fewer satellites than expected. This gap between theory and reality has sparked intense debate among scientists, leading to a search for explanations that could reconcile the two. One possibility is that many of these satellite galaxies are simply too faint for us to detect with current technology. Dark matter halos might host ultra-faint galaxies that emit very little light, making them nearly invisible to our telescopes. If this is the case, future advancements in observational technology could help us uncover these hidden cosmic neighbors, bringing the observed numbers closer to theoretical predictions. Another intriguing explanation involves the nature of dark matter itself. If dark matter is warm rather than cold, meaning its particles move at higher speeds, it could suppress the formation of small-scale structures like satellite galaxies. Warm dark matter would result in fewer, larger halos, potentially explaining why we see fewer satellites than expected. This idea challenges the traditional view of dark matter as cold and slow-moving, opening up new avenues for research and discovery. There's also the possibility that some satellite galaxies have been disrupted or destroyed over time. Interactions with the Milky Way's gravitational pull or collisions with other galaxies could have torn these smaller systems apart, leaving behind only faint traces or streams of stars. If true, this would mean that the missing satellites aren't missing at all, they've simply been erased from the cosmic map by the relentless forces of the universe. Despite these theories, the missing satellite problem remains one of the most compelling mysteries in modern astrophysics. It challenges our understanding of dark matter, galaxy formation, and the very fabric of the universe. As we continue to refine our models and improve our observational tools, we may finally uncover the truth behind this cosmic puzzle, shedding light on the hidden workings of the cosmos. With this mystery still lingering in our minds, we now turn to another enigma, the uneven distribution of dark matter across the universe. This next section will explore how dark matter's patchy presence shapes the cosmos and what it reveals about the nature of this elusive substance. Now turning to the cosmic puzzle of dark matter's uneven distribution, we find ourselves staring at a patchwork of mystery. Unlike the smooth, uniform spread we might expect, dark matter clumps together in dense regions while leaving vast, almost empty voids in between. This unevenness isn't just a random cosmic quirk. It's a fundamental clue to understanding how the universe evolved and how galaxies came to be. To grasp why this matters, let's start with the early universe. After the Big Bang, dark matter began to clump together under the influence of gravity, forming a cosmic scaffold. Ordinary matter, like gas and dust, followed this dark matter blueprint, eventually collapsing into the dense regions to form stars and galaxies. But here's the twist: dark matter didn't spread out evenly. Instead, it formed a web-like structure with dense filaments connecting massive clusters and leaving behind enormous voids. This cosmic web is the backbone of the universe, and its unevenness has profound implications. One of the most striking effects of this patchy distribution is its impact on galaxy formation. In regions where dark matter is densely packed, galaxies tend to form more readily, creating bustling cosmic cities. But in the voids where dark matter is sparse, galaxies are few and far between. This unevenness helps explain why we see galaxy clusters and superclusters surrounded by vast, empty spaces. It's as if the universe is a giant sponge, with dark matter filling the holes and ordinary matter following suit. But what does this tell us about dark matter itself? For one, it suggests that dark matter doesn't interact with itself or with ordinary matter in the same way that particles we're familiar with do. If it did, we might expect a smoother distribution, with dark matter spreading out more evenly over time. Instead, its clumpy nature hints at something more elusive, a substance that's influenced almost entirely by gravity and nothing else. This makes dark matter incredibly difficult to study directly, but its uneven distribution gives us indirect clues about its behavior. Another fascinating aspect of this mystery is how it challenges our understanding of the universe's expansion. The voids where dark matter is scarce seem to expand faster than the dense regions. This uneven expansion could be tied to dark energy, the mysterious force driving the universe's accelerated growth. By studying the distribution of dark matter, scientists hope to uncover the relationship between dark matter and dark energy, two of the greatest enigmas in modern cosmology. As we piece together the puzzle of dark matter's distribution, we're not just mapping the universe, we're uncovering the rules that govern its structure. From the dense clusters that birth galaxies to the vast voids that stretch between them, dark matter's uneven spread is a testament to the complexity of the cosmos. And as we continue to explore this mystery, we move closer to understanding the invisible force that shapes everything we see. With this uneven cosmic tapestry in mind, we now shift our focus to another intriguing question. How does dark matter influence the arrow of time? This next section will delve into speculative theories about dark matter's role in the universe's expansion and the flow of time itself. Now, as we venture into the realm of time itself, we encounter one of the most speculative and thought-provoking mysteries of dark matter, its potential role in the arrow of time. The arrow of time, the concept that time moves in one direction from past to future, is a fundamental aspect of our universe. But could dark matter, the invisible force shaping the cosmos, also influence how time flows? To begin, let's consider entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time, giving us the familiar arrow of time we experience. But here's where dark matter enters the picture. Some theories suggest that dark matter, with its gravitational influence, could play a role in how entropy evolves on a cosmic scale. Imagine dark matter as a hidden hand, subtly guiding the universe's expansion and the distribution of energy, which in turn affects the flow of time. One intriguing idea is that dark matter's uneven distribution, which we explored earlier, might contribute to the universe's overall entropy. In regions where dark matter is densely packed, the gravitational pull could slow down the expansion of space, creating pockets of lower entropy. Meanwhile, in the vast voids where dark matter is sparse, space expands faster, potentially leading to higher entropy. This unevenness could create a cosmic tug-of-war, influencing how time itself progresses in different parts of the universe. But the connection between dark matter and the arrow of time doesn't stop there. Some physicists speculate that dark matter could be linked to the very fabric of space-time. If dark matter interacts with space-time in ways we don't yet understand, it might affect the rate at which time flows. For instance, in regions with high concentrations of dark matter, time could pass more slowly compared to areas with less dark matter. This idea, while speculative, opens up fascinating possibilities for understanding the nature of time itself. Another angle to consider is dark matter's potential role in the universe's ultimate fate. If dark matter influences the expansion rate of the universe, as some theories suggest, it could also impact how entropy evolves over billions of years. A universe dominated by dark matter might experience a different trajectory of entropy increase, altering the arrow of time in ways we can only begin to imagine. While these ideas remain speculative, they highlight the profound connections between dark matter and some of the deepest mysteries of the cosmos. From shaping galaxies to influencing the flow of time, dark matter continues to challenge our understanding of the universe. As we explore these theories, we're reminded that the arrow of time isn't just a feature of our everyday lives. It's a cosmic phenomenon shaped by forces we're only beginning to uncover. With these speculative theories in mind, we now turn to another fascinating mystery, the potential connection between dark matter and neutrinos. This next section will explore why neutrinos are often considered a cousin to dark matter and what this could mean for our understanding of the universe. Now, as we shift our focus to the subatomic realm, we encounter a fascinating mystery that bridges the gap between dark matter and one of the most elusive particles in the universe, neutrinos. These ghostly particles, often referred to as the cousins of dark matter, share some striking similarities, yet their connection remains one of the most intriguing puzzles in modern physics. Neutrinos are nearly massless particles that barely interact with ordinary matter, making them incredibly difficult to detect. They stream through the universe in vast numbers, passing through planets, stars, and even our bodies without leaving a trace. This elusive nature has led scientists to draw parallels between neutrinos and dark matter, which also interacts weakly with ordinary matter and remains invisible to our telescopes. But the similarities don't end there. Both neutrinos and dark matter are thought to have played a crucial role in shaping the early universe, influencing the formation of galaxies and the large-scale structure of the cosmos. One of the most compelling reasons neutrinos are considered a cousin to dark matter lies in their shared mystery. While we know neutrinos exist, thanks to experiments like those detecting solar neutrinos, their exact properties, such as their masses and how they fit into the standard model of particle physics, remain unclear. Similarly, dark matter's fundamental nature continues to elude us despite decades of research. This shared enigma has led physicists to explore whether neutrinos and dark matter might be connected in ways we don't yet understand. One intriguing possibility is that dark matter particles could interact with neutrinos in subtle ways. For example, some theories suggest that dark matter might decay into neutrinos, or that neutrinos could act as a mediator between dark matter and ordinary matter. If such interactions exist, they could provide a new window into understanding both dark matter and neutrinos. Experiments like IceCube, which detects high-energy neutrinos from deep space, are already searching for signs of these interactions, hoping to uncover clues that could solve both mysteries at once. Another angle to consider is the role of neutrinos in the early universe. During the first moments after the Big Bang, neutrinos were among the most abundant particles, influencing the distribution of matter and energy. If dark matter particles were also present at this time, they might have interacted with neutrinos in ways that left an imprint on the universe's structure. By studying the cosmic microwave background and the distribution of galaxies, scientists hope to find evidence of these ancient interactions, shedding light on both dark matter and neutrinos. The potential connection between dark matter and neutrinos also raises profound questions about the nature of physics itself. If these two elusive entities are linked, it could hint at new forces or particles beyond the standard model. Such a discovery would not only revolutionize our understanding of the universe, but also open up entirely new avenues for exploration in particle physics. As we delve deeper into this mystery, we're reminded that the universe is full of hidden connections waiting to be uncovered. The relationship between dark matter and neutrinos, while still shrouded in uncertainty, offers a tantalizing glimpse into the intricate web of forces that shape our cosmos. And with each new discovery, we move closer to unraveling the secrets of these ghostly particles and their role in the grand tapestry of the universe. With this exploration of neutrinos and dark matter, we now turn to the final mystery in our journey, the ultimate fate of dark matter. This next section will examine what the future holds for this enigmatic substance and what it means for the destiny of the universe itself. As we step into the final chapter of our exploration, we confront one of the most profound questions in cosmology: what is the ultimate fate of dark matter? This enigmatic substance, which has shaped the universe since its earliest moments, holds the key to understanding not just the past and present, but also the future of everything we know. Will dark matter persist forever, silently guiding the cosmos, or will it eventually decay, altering the very fabric of reality? Let's delve into the theories that attempt to answer this cosmic question. One possibility is that dark matter is eternal, remaining stable over unimaginable timescales. If this is true, it means dark matter will continue to influence the universe indefinitely, shaping the formation of galaxies and the large-scale structure of the cosmos. In this scenario, dark matter would act as a silent architect, ensuring that the universe evolves in ways we can only begin to comprehend. Its gravitational pull would remain a constant force, even as stars burn out and galaxies drift apart over billions of years. However, not all scientists believe dark matter is immortal. Some theories suggest that dark matter particles could decay into other particles over time. If this happens, it could have dramatic consequences for the universe. For instance, if dark matter decays into lighter particles, it might release energy that could influence the expansion rate of the universe. This could either accelerate the expansion, leading to a colder, emptier cosmos, or slow it down, potentially altering the fate of galaxies and clusters. Another intriguing idea is that dark matter could transform into something entirely different. Some models propose that dark matter particles might interact with each other in ways that cause them to annihilate, producing bursts of energy or even new forms of matter. If this occurs, it could lead to a universe where dark matter gradually fades away, leaving behind a cosmos dominated by ordinary matter and radiation. Such a transformation would fundamentally change the balance of forces that govern the universe, with implications we can only begin to imagine. The ultimate fate of dark matter also ties into the broader question of the universe's destiny. If dark matter persists, it could play a crucial role in determining whether the universe continues to expand forever or eventually collapses in a big crunch. On the other hand, if dark matter decays or transforms, it might tip the scales toward a different outcome, such as a big freeze, where the universe becomes cold and lifeless over trillions of years. Understanding dark matter's fate is therefore essential to predicting the long-term future of the cosmos. As we ponder these possibilities, it's clear that dark matter remains one of the greatest mysteries in science. Its ultimate fate is not just a question of curiosity, but a key to unlocking the secrets of the universe's evolution. Whether it endures forever or fades away, dark matter's story is deeply intertwined with our own, shaping the cosmos in ways we are only beginning to understand. With this final mystery, we conclude our journey through the cosmic dark matter era. From the invisible web that binds galaxies to the ghostly particles that may hold the key to its nature, dark matter continues to challenge and inspire us. As we look to the future, one thing is certain: the quest to unravel its secrets is far from over, and each discovery brings us closer to understanding the universe's grand design. Thank you for joining us on this cosmic adventure. If you enjoyed this exploration, don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of the universe. Until next time, keep looking up. As we bring our journey through the cosmic dark matter era to a close, it's impossible not to marvel at the sheer scale of what we've uncovered and how much remains hidden. From the invisible cosmic web that binds galaxies together to the elusive particles that may make up dark matter, each mystery has revealed just how little we truly understand about the universe. These 25 enigmas remind us that dark matter is not just a scientific curiosity, but a fundamental force shaping the cosmos in ways we are only beginning to grasp. We've explored how dark matter influences galaxy formation, drives cosmic expansion, and even challenges our understanding of time itself. Yet, for every question answered, countless more arise. Where did dark matter come from? What is its ultimate fate? And could it hold the key to unlocking even greater mysteries, like the nature of the multiverse or the arrow of time? The more we learn, the more we realize how much there is still to discover. This journey has shown us that dark matter is not just a puzzle for scientists, it's a story that belongs to all of us. It's a reminder that the universe is vast, mysterious, and full of wonders waiting to be uncovered. So, as we conclude this exploration, we leave you with a question. What do you think lies beyond the veil of dark matter? Could the answers to these mysteries reshape our understanding of reality itself? Share your thoughts in the comments below, and let's continue this cosmic conversation together. If you've enjoyed diving into these mysteries with us, don't forget to like, subscribe, and hit the notification bell for more deep dives into the wonders of the universe. The quest to understand dark matter is far from over, and we can't wait to explore what's next with you. Until then, keep looking up, because the cosmos is full of secrets just waiting to be revealed.